Okay, power supply fans, let's take a look at the details of testing power transformers. Power transformers are generally a black box. They're rated at input and output voltage, in this case 117 in, 24 AC out, and 5 amp. That doesn't tell us much. All that tells us is a maximum permissible load power. I'm going to be using this for the grid, the G1 power supply for the microwave oven tube tester, and the voltage and currents out of this supply need to be continuously adjustable from 0 to 100 volts DC at a max of 120 milliamps at 40 volts DC. Very nonlinear, very weird. I can't use solid state regulation on the secondary of the transformer because that goes to a tube to a grid that's tenths of an inch away from a plate at 2000 volts. If there's a flashover, it'll probably destroy the regulation. So for isolation, I'm going to isolate the AC line over to the tube tester control panel, and I'm going to put a potentiometer or rheostat in the primary to adjust the secondary voltage. It's strange, but that keeps my hands and that circuit away from the grid circuit, which may be at high voltage, and puts a transformer in between. It's a kind of a safety. The maximum grid load is 6 watts. This is a 65 watt transformer, way oversized. So probably not practical, but it's what I have here for testing. The characteristics of the transformer I need to know are the unloaded secondary voltage, or the open circuit secondary like that, nothing connected to it. I need to know the loaded secondary voltage with a 6 watt load, which turns out to be about 100 ohms and a 10 watt resistor, sandstone. I need to know the percent efficiency of the transformer, which, as I mentioned in the MOT microwave oven transformer videos for these old school iron or steel transformers, is 50 to 60%. It's really bad. Half the power is wasted, but they're cheap. I also need to know something that we normally don't care about if we just plug the primary of the transformer into the AC line, and that's the parasitic current drawn by this transformer sitting there doing nothing. There's an unloaded secondary voltage, there's an unloaded secondary, and a primary current. Just plugging this transformer into the AC line draws current, and it's completely wasted. That amounts to a 0% efficiency of the transformer because there's nothing happening on the secondary. When the secondary is loaded, all that's going to change. So I got to know how it's going to change. So first step, get a decent digital multimeter. That isn't one, but it's cheap. For convenience, I've got an amp clamp like used in HVAC, transformer, cheater cord. Of course, no fuse. We know what we're doing, don't we? So we plug that puppy in, and we read across the primary 124.6 volts AC from the AC line. And with a current clamp and one wire to the transformer, we read this transformer is wasting 76 milliamp at 124.5 volts AC. That's power doing nothing except heating the copper windings in the core. Thing to be very careful with is to notice that when I take the amp clamp and I put it near the transformer, which has magnetic field, I start reading more current wasted by the current clamp, and there's no load current. So what that's doing is that this magnetic circuit of the current clamp is coupling with the magnetic fields in this transformer. So the transformer is not shielded. So what that tells us indirectly is that this current clamp can be used to tell what the extents of the magnetic field are and the orientation. In that orientation, that far away, there's no coupling. So if there's other circuits or devices that we can't have 60 hertz from this coupling to, we can use this for a cheap field indicator to tell how far away to move them. That's important in things like audio amplifiers, where we'd probably put this under the chassis or in a different enclosure. So if using a current clamp to measure the AC line here, you got to make sure the current clamp is far enough away not to have that current added, because that'll cause a real error in the actual current of the transformer. This measures about 79 mils. I used the meter. It's actually 75, close enough. Of prime importance is the secondary voltage, open circuit, and loaded, and that gives us the percent regulation. Open circuit secondary, 28.8 volts AC for what was it, 124 and change on the primary. And that gives approximately the step up, the turns ratio. It's about 3.63. So when that secondary is loaded, we'll expect that voltage to drop a little bit. Okay, there's a 100 ohm, 10 watt sandstone resistor connected to the secondary, and the secondary voltage is 28.63. It dropped about 0.2 of a volt. That is extremely good regulation. This is what you might call passive regulation. It's not a transistor voltage regulator. That regulation comes from the transformer being very much oversized for the load. A much smaller transformer, volt amp wise, would have a much bigger drop. It's similar to this primary drawing 79 milliamps off an AC line that can supply 20 amp. The AC line will never notice it. So it's a thing of magnitudes and percentages. So the reason that's important is that when the tube grid's connected, I don't want the voltage changing. If it does, then I'd have to reach over and change the control to change the voltage back to what it should be. So that's good. The problem is I'm going to adjust the output voltage with a potentiometer or a rheostat in the primary. And that oversized transformer drawing 80 milliamps is very bad because that makes a lot of excess heat in the pot or the rheostat controlling the primary. It's going to get hot. So in reality, I'm probably going to choose a transformer that's about 10 or 12 VA for a 6 VA load instead of this 65, which is 10 times too much. And that'll greatly reduce the parasitic primary current. Those are the circuit measurements. Here's a diagram of the primary. I've measured with an inductance and resistance meter. The primary is 370 millihenry at 5.7 ohms. That's a total impedance of 139.5 ohms. The unloaded primary current is 79 milliamp at 124 volts AC. 124 volts AC divided by 79 milliamp is not anywhere near the impedance of the primary. So we can't use this information to find a primary inductance or impedance, because 123 volts and 79 milliamps, which we know are accurate, means the primary is 1557 ohms, not 139. That's more than a 10 times error. Why? Well, resistance is resistance. The problem here is that this LCR meter, nice LCR meter for measuring windings this big, is lying to me. It says that primary is 370 millihenry, and it can't be. Why? Why is that perhaps a 10 times error, or there's some other error source that's that big? Well, it's quite possible because that LCR meter is testing at about, I think it's about 5 kilohertz. And this is a 60 cycle transformer. So the transformer is probably eating a lot of the energy from the test meter. So we can't trust that. So inductance measurements are pretty much useless unless we do it at 60 cycles. That transformer primary is wasting 124 volts times 79 milliamps, which is 9.8 watts, just burned up in heat, useless. The secondary open circuit, 28.6 volts AC, that doesn't tell us much. That does give us basically a step up or step down ratio, which is the ratio of the voltages. So, interesting, not mainly what we're after. With 100 ohm load, 10 watts, the secondary is 28.4 volts. 28.4 divided by 100 is 285 milliamp, which is 8.1 watts. There's more power wasted in the transformer than the load. The primary current with the 100 ohm load was measured at 126 milliamp and 123.6 volts AC. The primary voltage didn't drop a bit. It could care less about 120 mils. That's a total of 15.6 watts. That doesn't add up to total. So those numbers are off a bit. See, something's changed with the load. The primary is 126, 123.6 volts times 126 milliamps, 15.6 watts. The secondary load is calculated at 8.1 watts. So that gives us an apparent efficiency of 52%, which is pretty bad. And this is what drove the change to go to switch mode power supplies, which are upwards of 97% efficiency for light loads, because this starts adding up to some utility power losses when there are hundreds of millions of devices with transformers in them. The calculated figure for the parasitic primary current of 79 mils was 9.7 watts. So that's a 5.9 watt difference. So that measured primary current with the unload secondary of 9.7 plus 18 or plus 8.1 equals 17.8, not 15.6. So there's been an apparent increase in efficiency by loading the transformer. Nothing we can do really with or about that. It's just interesting to notice. So 52% efficiency, frowny face, sucks. A switch mode power supply for this low power would be 95, 97% efficiency. Huge difference. But I can't put a switch mode power supply up against a high voltage source. Secondary regulation. Unloaded 28.6 volts, loaded 28.4. That's a 0.7% regulation, which is extremely good. That means if I set this power supply to 40 volts and then connect the grid of the tube and the tube starts operating, the voltage won't change. Therefore, I won't have to go back when the tube comes on and change the voltage. And I won't have to sit there and juggle adjusting 3 knobs and reading 2 meters. Now this is still going to be subject to changes in the AC line voltage, which are give or take 10%. But that changes either relatively slowly or at times of the day, like evening when people come home, start turning loads on. The line voltage might drop sharply at 5 or 6 p.m. So do this testing midday, and the AC line is going to be pretty stable. It's been a couple hours. It's only varied about a volt, which is a little better than 1%. So overall, this will be a very well regulated system. But it won't have any solid state devices in it except high voltage diodes. So there's how to figure out all these problems and properties of a transformer where the manufacturer won't or can't give them to you. As you can see, it changes by the load, so they could give you graphs, but pretty much have to find this out on our own with whatever application and whatever load are necessary. Interesting thing to note, the apparently grossly incorrect reading of primary inductance when a LCR meter, which I've measured at 5 kilohertz on some certain range, was connected to that transformer. That transformer is either iron or cheap steel laminates. Apparently that core has shunted out and consumed that 5 kilohertz energy. Well, what that means is that the 60 hertz transformer has effectively become an RF choke. Now, 5 kilohertz is not RF yet, but it's a 5 kilohertz square wave, and that has RF components. So what we've got here is effectively an RF choke. So, and that's how line reactors work. The old ones are just inductors wound on iron cores. So, little observation leads to another use of that transformer possibly for some RF proofing. That property, that loss, may help keep RF on the secondary and the power supply from getting back to the AC line. That's very important, so that there's a lack of conducted interference. So that's about everything practically needed to analyze that transformer for a power supply application. And at a 50% efficiency, you can see it makes a big difference. So there you go, KBYP, happy power supplying.